The Hubble tension is one of the most pressing mysteries in modern cosmology, centering on a deceptively simple question: how fast is the universe expanding? What appears to be a straightforward measurement has evolved into a profound scientific crisis, as different methods yield incompatible answers. This inconsistency challenges our most fundamental understanding of the cosmos. At the heart of the issue are two independent ways of calculating the Hubble constant, the number that describes the expansion rate. The first method relies on observing nearby objects such as Cepheid variable stars and type Ia supernovae, then extending those measurements outward to calibrate cosmic distances. The second approach comes from observations of the cosmic microwave background, the faint afterglow of the Big Bang, which encodes information about the early universe. Ideally, these two methods should agree. Instead, they diverge significantly. Local measurements suggest a faster rate of expansion, while early universe calculations point to a slower one. This discrepancy has become a central puzzle because both techniques are considered highly reliable, yet their answers are mutually incompatible. If the tension is real and not due to overlooked errors, it implies that something is missing from our current cosmological models. The mystery is whether this conflict reflects new physics, perhaps undiscovered particles, modified dark energy, or even a breakdown of our current understanding of gravity, or whether subtle errors still lurk in the data. Numerous attempts have been made to reconcile the results, from recalibrating supernova distances to refining cosmic microwave background models with the help of modern telescopes such as Hubble, Planck, and JWST. Yet no single solution has convincingly resolved the gap. Today, the Hubble tension remains an open and divisive question. Resolving it could revolutionize our picture of the universe, forcing us to reconsider the laws of physics that describe space, time, and cosmic evolution itself. Dark matter represents one of the most enduring enigmas in modern physics, an invisible substance that makes up about 80% of all matter in the universe, yet cannot be directly detected. Its presence is inferred from its gravitational effects. Galaxies rotate faster than visible matter alone can explain. Clusters of galaxies bend light in ways that suggest hidden mass, and the large-scale structure of the cosmos requires its unseen hand. Despite overwhelming evidence for its existence, the true nature of dark matter remains unknown, making it one of the greatest unsolved problems in science. The mystery lies in its elusiveness. Unlike ordinary matter, dark matter does not emit, absorb, or reflect light, making it invisible to telescopes. Its lack of interaction with electromagnetic forces means it slips past every particle detector built so far. Yet, without dark matter, our current cosmological models would collapse. Why something so abundant and fundamental remains hidden challenges both observational astronomy and theoretical physics. Scientists have proposed numerous candidates, from exotic particles such as weakly interacting massive particles and axions to the possibility that dark matter could consist of primordial black holes. Recent theories push the boundary further, suggesting that dark matter might arise naturally from the early universe. Some researchers propose a mirror world, a hidden sector with its own forces and particles that never interact with ordinary matter except through gravity. Others explore whether dark matter could have been produced by quantum processes at the edge of the rapidly expanding universe after the Big Bang. Despite decades of effort, including massive underground detectors, space missions, and collider experiments, no direct evidence has confirmed any candidate. This persistent silence deepens the mystery. Today, dark matter remains central to cosmology and particle physics alike. Solving it would not only explain what binds galaxies together, but could also uncover entirely new sectors of reality, reshaping our understanding of the universe at its most fundamental level. Few mysteries are as profound as what lies inside a black hole. Defined by their immense gravity, black holes warp space and time so drastically that nothing, not even light, can escape beyond a boundary known as the event horizon. At their core is thought to be a gravitational singularity, a point of infinite density and zero volume where the known laws of physics break down. This makes the interior of a black hole one of the greatest unknowns in science, pushing the limits of both general relativity and quantum theory. General relativity predicts that matter falling into a black hole collapses into the singularity, where gravity becomes infinitely strong. For an infalling object, this journey would involve extreme spaghettification, as tidal forces stretch it thinner and thinner until it vanishes into the singularity. However, an observer at a safe distance would never actually see the object cross the horizon. Instead, it would appear to freeze in time, slowly fading from view. This contradiction highlights the peculiar clash between perception, relativity, and reality. The central mystery is that singularities imply a physical impossibility, infinities in density and curvature. Physicists generally take this as evidence that general relativity, while powerful, is incomplete in such extreme conditions. The real solution likely requires a unified theory of quantum gravity, capable of merging Einstein's relativity with quantum mechanics. Some models propose that singularities might be replaced by exotic structures, or that new states of matter could exist inside. Others explore whether black holes might hide naked singularities or bridge to other universes through wormholes, though these remain highly speculative. Despite decades of study, no observation can directly probe the interior of a black hole, as the event horizon forever shields it. This inaccessibility makes the question of what lies inside simultaneously frustrating and captivating. Solving it could reveal not only the true fate of matter, but also the fundamental structure of space, time, and reality itself. Dark energy is perhaps the most baffling force in the universe, a mysterious phenomenon responsible for the accelerated expansion of space itself. First uncovered in 1998 through observations of distant supernovae, it now accounts for nearly 70% of the cosmos, yet scientists still have no clear idea what it actually is. Its presence is undeniable, but its nature defies every expectation of physics. At its core, dark energy is the name given to the repulsive effect that counteracts gravity on the largest scales. Instead of slowing down under its own mass, the universe has been expanding faster and faster over time. To explain this, cosmologists often picture galaxies as raisins in dough. As the dough rises, the raisins move farther apart. But with dark energy, the dough seems to rise with ever-increasing speed, as if some hidden engine is driving it forward. The mystery deepens because nothing in known physics behaves this way. Energy typically dilutes as the universe expands, yet dark energy appears constant, or may even evolve across cosmic time. One possibility is that it is Einstein's cosmological constant, a built-in property of empty space. However, quantum field theory predicts a value for this constant that is staggeringly larger than what we observe, creating one of the greatest mismatches in science. Alternative theories suggest quintessence, a dynamic field that shifts with time, or even that our understanding of gravity itself needs rewriting. Efforts like the Dark Energy Spectroscopic Instrument and the Atacama Cosmology Telescope are probing whether dark energy changes with time, but results so far are conflicting. Some hint at evolution, while others confirm the standard model. For now, dark energy remains unsolved. Cracking this mystery could reveal the universe's ultimate destiny, whether it expands endlessly into darkness, stabilizes, or collapses back in on itself in a cosmic finale. The nature of the Big Bang remains one of the greatest mysteries in cosmology. While it is widely accepted as the event that set our universe into motion, the details of what actually happened, or whether the Big Bang was truly the beginning, are still unresolved. Understanding this is essential because it touches on the very origin of space, time, matter, and the physical laws themselves. Traditionally, the Big Bang refers to a moment when the universe was extremely hot, dense, and compact, expanding outward into the cosmos we see today. This model is supported by strong evidence. The discovery of the cosmic microwave background, the observed expansion of galaxies, and the abundance of light elements predicted by nuclear physics. These confirm that the early universe was once in a hot, dense state. However, the notion of a singularity, a point of infinite density and temperature where physics breaks down, creates more questions than answers. The puzzle is whether the Big Bang was truly the beginning, or simply a transition from something that came before. Extrapolating backwards suggests a singularity, but such infinities usually indicate that our theories are incomplete. Modern research suggests the hot Big Bang may not have been the ultimate start, but rather the aftermath of an earlier phase, such as cosmic inflation. If so, the universe may have existed in another state before the hot expansion, raising the possibility of a pre-Big Bang universe or even cycles of expansion and collapse. Attempts to clarify this mystery include inflationary models, quantum gravity approaches, and alternative scenarios like the Big Bounce or black hole origin models. Observations of the cosmic microwave background and large-scale structure continue to test these theories, but none have yet provided definitive answers. Today, the nature of the Big Bang remains unresolved. Was it the first moment of time, or a doorway to something older and deeper? Solving this mystery would not only explain how the universe began, but could also reveal whether ours is a singular cosmos or part of an endless cosmic cycle. The origin of matter is one of the deepest mysteries of the universe, raising a simple yet profound question. Why does anything exist at all? After the Big Bang, the cosmos was filled with a hot, dense soup of particles and radiation, yet somehow from that chaos emerged the protons, neutrons, and electrons that form stars, planets, and life itself. In cosmology, matter refers to the particles that make up everything we see. Atoms built from protons and neutrons, bound by forces described in particle physics. The challenge is that the early universe was so hot, nearly 250,000 times hotter than the sun's core, that such structures should have been impossible to form. Yet within fractions of a second, quarks and gluons condensed into the building blocks of matter, eventually leading to galaxies and biological life. Understanding how this transition happened is essential for explaining our very existence. The puzzle lies in the details. When scientists recreate early universe conditions using particle accelerators, they find unexpected complexities. Much of the matter detected may not come directly from the primordial quark-gluon plasma, but from later reactions as the universe cooled. Recent calculations suggest that as much as 70% of certain observed particles are formed in these later processes rather than the original first moments. This complicates the picture and raises new questions about how much of today's matter truly emerged from the initial cosmic fireball. To address this, physicists study rare particles like charmonium, created in high-energy collisions. These experiments, alongside advances in nuclear physics, refine models of how matter crystallized from energy. Yet no explanation fully resolves the transition from a formless plasma to the ordered material universe. The origin of matter remains unsolved, but its importance cannot be overstated. Cracking this mystery would not only illuminate the universe's first seconds, but also answer the ultimate question of why something exists rather than nothing. Quantum gravity is the name given to one of the greatest puzzles in modern physics: how to combine general relativity, our best theory of space and time, with quantum mechanics, our most successful description of matter and energy. Both theories are remarkably accurate, yet when applied together in extreme conditions like black holes or the Big Bang, they break down. This clash leaves us without a complete picture of reality. At its core, quantum gravity is the search for a single framework that unifies the large universe of curved spacetime with the small world of particles and fields. General relativity explains how gravity shapes the cosmos, while quantum theory governs subatomic behavior. Both claim universality, but each fails where the other dominates. For example, relativity predicts singularities of infinite density, while quantum mechanics demands uncertainty and discreteness. These contradictions highlight why quantum gravity is not optional but necessary. The mystery lies in the fact that no experiment directly requires quantum gravity today. Instead, it is a problem born of theory itself. How does time emerge when relativity and quantum mechanics disagree about its meaning? Does spacetime itself come in discrete units like particles? And what truly happens inside black holes? These unanswered questions keep the search alive. Physicists have attempted many routes toward resolution. String theory suggests the universe is made of vibrating one-dimensional objects. Loop quantum gravity proposes space-time is woven from tiny loops. Other approaches explore causal sets, asymptotic safety, or emergent gravity. Each offers insights, but none yet provides a complete, testable theory. Today, quantum gravity remains a frontier of speculation and creativity. Solving it could explain the origin of the universe, the ultimate fate of black holes, and perhaps unify all forces of nature. Until then, it stands as physics' most enduring mystery, where the very fabric of reality waits to be revealed. The nature of time is one of the greatest mysteries of the universe, because we all experience its flow, yet science cannot fully explain what it really is or why it exists at all. Time shapes every aspect of reality, but its true essence continues to puzzle both physicists and philosophers. From a scientific standpoint, time is usually defined as the measure of change and sequence, past, present, and future. In everyday life, clocks and calendars track it, while in physics, time is a fundamental parameter woven into the fabric of space-time itself. General relativity shows that time bends under gravity, while quantum mechanics treats it as a background stage for events Despite these definitions, no consensus exists on whether time is a universal feature of reality or just a human construct to describe change. The mystery deepens because time behaves strangely under different theories. Relativity suggests that time is relative, stretching and slowing depending on speed and gravity. Quantum theory, however, often works without time at all, treating events as probabilities rather than unfolding moments. Even more puzzling is whether time has a beginning, as in the Big Bang, or whether it is eternal. Does the flow of time actually exist, or is it an illusion created by human perception? Attempts at solving the puzzle span physics and philosophy. Some researchers propose that time emerges from deeper physical processes, while others argue it is the most fundamental reality of all. Lee Smolin and Roberto Unger, for example, insist that time is not a byproduct, but the most real feature of the universe. Competing theories like block universe models claim past, present, and future all coexist, eliminating the idea of flow altogether. Yet no approach has been able to fully resolve the contradictions. Today, the nature of time remains an open question. Understanding it could transform not only cosmology, but also our view of existence itself, reshaping how we think about beginnings, endings, and the very structure of reality. The origin of life is one of the deepest mysteries of science, because although we know life exists in a dazzling complexity today, no one can explain with certainty how the first living systems emerged from lifeless chemistry. Understanding this puzzle matters because it touches not only biology but also cosmology, evolution, and even the search for life beyond Earth. Scientists define this question under the term abiogenesis, the natural process by which life arises from non-living matter. Unlike evolution, which explains how life changes and diversifies once it exists, abiogenesis asks how the very first cell-like systems appeared around 4 billion years ago. This is especially difficult because the earliest traces of life left no fossil record, leaving only indirect chemical clues locked in ancient rocks. The mystery lies in bridging the gap between simple molecules and self-replicating systems. Amino acids and nucleotides, the building blocks of proteins and RNA, can form under certain conditions, as shown in classic experiments like Miller-Urey. But how these pieces assembled into larger chains capable of reproduction remains unsolved. Water itself, abundant on early Earth, makes the spontaneous linking of long RNA strands thermodynamically unlikely. Some researchers argue life may have begun in volcanic vents, icy environments, or even beyond Earth, later delivered by comets. Many theories attempt to fill this gap. The RNA world hypothesis suggests that early RNA molecules acted as both information carriers and catalysts, perhaps enclosed within primitive membranes. Recent laboratory advances have shown how certain RNA components could spontaneously assemble, yet a complete pathway remains missing. Other researchers propose life was seeded from space, or that improbable events were inevitable given the vastness of the universe. Each approach, however, faces unresolved contradictions. Today, the origin of life remains unsolved but is a rapidly advancing field. Discoveries continue to push the timeline of Earth's earliest life further back, suggesting it may have arisen surprisingly quickly once conditions stabilized. Solving this mystery would reshape our understanding of biology, evolution, and our place in the cosmos, showing whether life is a universal outcome of nature or an extraordinarily rare event. The fine-tuning problem is one of the most striking mysteries in modern cosmology. It refers to the observation that the universe's fundamental constants, such as the strength of gravity, the charge of the electron, or the cosmological constant, appear to be precisely set within extremely narrow ranges that allow life to exist. Even a tiny deviation in these numbers would make stars unstable, prevent atoms from forming, or erase the possibility of complex chemistry, leaving a universe barren and lifeless. Scientists define fine-tuning as the sensitivity of physical laws to small changes in fundamental constants. For example, if the strong nuclear force were just a few percent stronger or weaker, the processes that forge carbon and oxygen in stars would fail, making life as we know it impossible. This raises the question, why do these values fall within such unlikely ranges? Are they simply accidents of chance, or do they reflect deeper principles yet to be discovered? The mystery lies in the improbability of it all. The laws of physics could, in principle, take on a vast range of values, but the set we observe seems just right for life. Some, like Fred Hoyle, interpreted this as evidence of a guiding intelligence, while others suggest that our universe is just one of countless universes in a multiverse, where we happen to exist in the rare one capable of sustaining life. Still, others argue that future physics may reveal hidden mechanisms that naturally constrain these constants. Attempts to solve the problem range from the anthropic principle, which emphasizes observer bias, to bold ideas like string theory, cosmological natural selection, or even the simulation hypothesis. Yet none of these explanations has gained universal acceptance, and direct empirical tests remain elusive. Today, the fine-tuning problem continues to fuel debates not only in physics but also in philosophy and theology. Resolving it could redefine our understanding of why the universe exists in its present form, and whether life is a cosmic accident or an inevitable outcome written into the very fabric of reality. Cosmic inflation is one of the great unsolved mysteries of cosmology. It proposes that in the earliest fraction of a second after the Big Bang, the universe underwent an unimaginably rapid expansion, growing exponentially faster than the speed of light. This idea was introduced to resolve puzzles that the original Big Bang model could not explain. Yet inflation itself raises profound questions that remain unanswered. At its core, inflation helps explain why the universe looks the way it does today. Without it, the cosmos should appear irregular, with regions too far apart to have ever exchanged information or energy. Instead, the universe is strikingly uniform in temperature and structure across vast distances. Inflation solves this by positing that everything we observe once existed in a much smaller connected patch of space that suddenly stretched outward. It also accounts for the large-scale distribution of galaxies and predicts subtle fluctuations in the cosmic microwave background, many of which have been confirmed by observations. The mystery lies in the mechanism. What exactly drove inflation? Physicists suggest a hypothetical inflaton field, but no direct evidence for such a field exists. Even deeper, inflation seems to lead naturally to the idea of a multiverse, where different regions of space inflate at different rates, potentially creating countless universes with varying physical laws. This raises philosophical as well as scientific challenges, because such universes may be forever beyond observation. Attempts to refine or replace inflation include new models that rely on quantum effects, bouncing cosmologies, or ideas like the recently proposed black hole universe, where our cosmos emerged from a collapse and rebound inside a larger parent universe. Each alternative offers intriguing insights, but none has achieved consensus. Today, cosmic inflation stands at a crossroads. It is one of the most successful theories for explaining the early universe, yet its foundations remain speculative. Resolving this mystery could not only clarify how the cosmos began, but also determine whether our universe is unique or merely one of many in an endless cosmic landscape. The fate of the universe is one of the deepest mysteries in cosmology, touching on the ultimate question of how everything will end. Scientists know the cosmos is expanding, but whether it will expand forever, slow down, or collapse remains uncertain. This problem sits at the intersection of physics, astronomy, and philosophy, shaping how we understand our place in the cosmos. At the heart of the debate is the balance between gravity and dark energy. Gravity, created by matter, works to pull everything inward, while dark energy drives the expansion of space itself. Observations since the late 1990s show that the expansion is not slowing, but accelerating, an unexpected discovery that radically altered cosmology. Yet, acceleration alone does not reveal the universe's long-term trajectory, leaving multiple possible outcomes on the table. The puzzle lies in the unknown nature of dark energy and the precise amount of matter in the universe. If dark energy remains constant, the cosmos may expand endlessly, galaxies drifting apart until stars die and black holes evaporate, a scenario often called the heat death or big freeze. If dark energy grows stronger, expansion could accelerate uncontrollably, tearing apart galaxies, stars, and even atoms in a big rip. Conversely, if dark energy weakens or reverses, gravity might halt expansion, triggering a collapse known as the Big Crunch. Some theories even suggest cycles of expansion and contraction, leading to a big bounce where new universes are born. Attempts to resolve these questions come from precise measurements of supernovae, galaxy distributions, and the cosmic microwave background. Experiments such as the Dark Energy Survey and the upcoming Euclid mission aim to pin down the properties of dark energy, but results so far remain inconclusive. Today, the ultimate fate of the universe is still undecided. Solving it requires not just new data, but breakthroughs in fundamental physics. The answer will determine whether our cosmos drifts into eternal silence, collapses in fire, or repeats in cycles, reshaping our deepest vision of existence itself. Thank you for watching this video. If you enjoyed, please leave a like and subscribe and let me know in the comments if you would like to see more videos like this one. Thanks again. Goodbye.